Welcome back to the deep dive. Today, we're going to look at a system that is simultaneously one of the most studied and yet one of the most consistently overlooked aspects of pharmacology. We're talking about the invisible infrastructure of the body.
It really is invisible to most people, I think even to many clinicians.
Yeah.
It's the difference between, looking at a city map and only seeing the roads
Right.
versus seeing the traffic lights, the toll booths, the border crossings, and all the security checkpoints.
I love that image. We tend to have this very, passive view of taking medication. You swallow a pill, it dissolves, it gets in the bloodstream, and it just sort of floats like a leaf on a lazy river, just drifting along until it bumps into the right organ and does its thing.
That's the lazy river fallacy. And if our bodies worked like that, honestly, we'd be dead in a day. We would be poisoned by our own waste products, or we would be starved of nutrients because they wouldn't get where they needed to go.
Because biology is, at its core, about control.
Precisely. Biology hates randomness. The reality is that the movement of almost every significant molecule in your body, whether it's the statin you took this morning for your cholesterol, or the dopamine in your brain regulating your mood, is rigidly controlled. It's handed off, bucket brigade style, from one protein to another.
And that is exactly what we are diving into today, this hidden border patrol of the cell. We're going to explore the world of membrane transporters. And to guide us, we're going to be synthesizing the heavy-hitting mechanistic detail from Goodman and Gilman's chapter on membrane transporters and drug response.
Chapter 5, yeah, the really deep molecular stuff.
Exactly. And pairing it with the clinical reality we see in Katzon, both from Chapter 3 on pharmacokinetics and Chapter 67, which is all about drug interactions.
And just to set the stage for the sheer scale of this whole operation, if you look at the human genome, we have, roughly 23,000 genes? Current estimates suggest that about 2,000 of them code for transporters or transporter-related proteins.
2,000. That's nearly 7% of our entire genetic code.
7%. I mean, just think about that investment. Evolution is ruthless. It doesn't keep things around that aren't absolutely necessary. It has decided that 7% of its total budget should be spent just on moving things across borders. This is not a niche side topic.
No.
This is a fundamental pillar of how life maintains homeostasis.
So our mission today is really to map this territory. We aren't just reading the textbook. We're trying to build a mental model. We want to understand not just that drugs move, but how they move, and more importantly, why that movement sometimes fails.
We want to move from just memorizing these long lists of interactions to actually understanding the machinery. Because if you understand the machine, you can often predict the interaction before you even look it up.
Okay, before we get into the weeds, let's do a front load. We always like to give the listeners the quick version right at the top. If you have to run in 5 minutes, what are the 5 absolute pillars you need to take away from this deep dive?
All right, let's lock these in. Pillar number 1. Transporters are active participants. They are not passive plotting. They actively determine if a drug gets into the brain, if it stays in the liver, or if it gets peed out. They can create massive, massive concentration differences between what's in the blood and what's in the tissue.
So the level of a drug in your blood doesn't necessarily equal the level of drug in, say, your brain cells.
Not even close. You could have low blood levels but toxic tissue levels, or the other way around, all depending on these transporters.
Okay. Pillar number 2.
The tale of two families. Broadly speaking, you've got 2 major clans. You have the ABC superfamily. Think of them as armor-plated bouncers. They use energy to pump things out.
Okay, the exporters.
And then you have the SLC superfamily, the salute carriers, which for the most part bring things in. So you have influx versus efflux.
In versus out. The importers and the exporters. That's simple enough. What's pillar 3?
Location is destiny. We call this vectorial transport because these transporters are bolted to very specific sides of a cell, the front door, or the back door, so to speak. They create a one-way flow. This is how the body moves drugs from the blood through a liver cell and straight into the bile. It's a directional assembly line.
Which would explain why if one of those doors breaks, the whole system just backs up.
Correct, which leads perfectly to pillar 4, the source of variability. Why does one patient take a statin and feel fine, while another patient on the exact same dose gets rhabdomyolysis and their muscles start to fail? We often blame metabolism, but so often it's actually a genetic typo in a transporter, a broken gate.
That's a huge one for personalized medicine. And the last one, pillar 5.
Pillar 5 is the hidden interaction. We're all trained to look for metabolic interactions, CYP450 inhibition, but many of the most dangerous, surprising toxicities happen because one drug blocked the transporter for another drug. You lock the exit door, the room fills up, and you get toxicity.
All right, that's the roadmap. Now let's build the car. We have to start with section 1, the hardware. You mentioned these two families, ABC and SLC. But before we get to the alphabet soup, I need to clear up a basic definition that I think trips a lot of people up. I tend to use the words channel and transporter interchangeably. Is that wrong?
It's, well, for our purposes, it is effectively wrong, yes. I mean, they're both proteins stuck in a cell membrane, and they both let things through, but they function on completely different timescales and by completely different mechanisms. It's like comparing a garden hose to a bucket brigade.
Okay, break that down for me.
So think of a channel like an ion channel that lets sodium or potassium into a nerve cell. It acts like a floodgate. It has a physical gate that just flicks open. When it's open, ions or water molecules just rush through in a massive stream driven purely by diffusion. We are talking about turnover rates of 10 to the 6 or even 10 to the 8 molecules per second.
Millions per second. So basically just a hole that opens and closes.
Pretty much. It's a stochastic event. It flickers open, there's a flood, it flickers closed. A transporter is totally different. It is a machine that has to physically handle the cargo. It has to bind to the specific molecule, a substrate form an intermediate complex, change its physical shape, and then release it on the other side.
So it's tactile. It has to grab, move, and then release.
Yes. Goodman and Gilman uses the term rocker switch, or gated pore, to visualize this. Imagine a V-shape opening to the outside of the cell. The drug floats in and lands in the V. The protein senses it, clunks shut at the top, rocks its whole shape, and then opens at the bottom, releasing the drug inside the cell.
That sounds, well, significantly slower.
Much, much slower. We're talking 1 to 10 to the 3 molecules per second, maybe 1,000 per second compared to millions for a channel.
Okay, but why does that speed difference matter to a clinician? Why should a doctor care about that millisecond difference in how these work?
Because of one critical concept, saturability. This is huge. Because the transporter has to physically shake hands with every single molecule it moves, there is a hard limit to how fast it can work. If you flood the system with too much drug, you run out of available transporters. The line backs up.
Ah, I see. With a channel, with a floodgate, it's almost impossible to overwhelm it because the flow is so fast. But with a transporter, which is basically a revolving door, you can easily get a traffic jam.
Exactly. And when you hit that limit, when you saturate the system, the kinetics change. You go from linear kinetics, where more drug means more movement, to nonlinear kinetics. And that's when blood levels can spike unpredictably because the doors are all full and the clearance system can't keep up.
Okay, that makes perfect sense. Transporters are saturable bottlenecks. Now let's meet the families who run these checkpoints. First up, the SLC superfamily. The salute carriers.
Right, this is the in crowd. It's a massive group, 52 families, nearly 400 distinct transporters, and their main job is influx, bringing things into the cell, things like nutrients, vitamins, glucose, and of course drugs.
How do they pay for this? I mean, moving things usually costs energy, right?
Great question. They are generally cheap to run. They utilize either facilitated diffusion or secondary active transport. Facilitated diffusion is just helping things flow downhill from a high concentration to a low concentration. It's like holding a door open for someone who's already walking that way. No real energy cost.
And secondary active transport, that sounds like it involves energy somehow.
It does, but it's clever. It's like carpooling. The cell spends a huge amount of energy burning ATP using a completely different pump, the sodium-potassium pump, to keep the sodium levels inside the cell very, very low. So the sodium outside the cell is desperate to get in. It's like water held back by a dam.
That's the sodium gradient we all learned about.
Right. And the SLC transporter takes advantage of that pressure. It basically says, okay, sodium, come on in, but you have to drag this drug molecule with you. The drug literally hitchhikes on the energy of the sodium rushing into the cell.
So the drug itself doesn't burn any ATP directly. It just cashes in the gradient credit the cell already established.
Exactly. It's an incredibly efficient system.
So who are the famous members of this SLC family that we really need to know?
You'll see these acronyms everywhere in Katzung and on FDA inserts. You have the OTs, organic anion transporters, and the OCTs, organic cation transporters. These handle small charged molecules. And then the very important OATPs, the organic anion transporting polypeptides.
OATPs,
Yeah.
the big liver ones,
Yeah.
right, for statins and things.
Mostly, yes. They're huge for getting drugs like statins out of the blood and into the liver where they work. And we can't forget the neurotransmitter movers, SERT for serotonin and DET for dopamine. They are all SLCs. They are all fundamentally importers.
Okay, so SLCs act like turnstiles or carpool lanes bringing things in.
Yeah.
Now let's talk about the other side, the bouncers, the ABC superfamily.
ABC stands for ATP binding cassette. And these represent the efflux side of the equation. Their job is almost always to get things out. And usually they're pumping things out against a massive concentration gradient.
So they can't just open the door and let things flow. They have to actively push.
No, they have to push hard. Imagine a basement that's flooding. The ground outside is soaking wet. It's saturated. You can't just open a drain. The water would flow in. You need a sump pump. You need to plug it into the wall and use electricity to physically force the water up and out against gravity and pressure.
And the electricity in this case is ATP.
Correct. These are primary active transporters. They have a little region, a cassette, that binds ATP, hydrolyzes it, literally burns the fuel to force the protein to change shape and physically shove the drug molecule out of the cell.
That implies they are really powerful.
Yeah, are incredibly powerful. They can maintain a concentration gradient of 100 to 1 or even higher. They can keep a cell virtually empty of a drug even if the blood outside is just swimming in it.
And who are the celebrities here? The big names in the ABC family.
The most famous is MDR1, also known as P-glycoprotein or PGP. That's the grandfather of them all. Then you have the MRPs, the multi-drug resistance proteins, and BCRP, the breast cancer resistance protein.
I'm noticing a theme in those names. Resistance. Multi-drug resistance. That sounds almost hostile.
It's a huge clue to their history. We didn't discover these by looking at healthy physiology, not initially. We discovered them because they were frustrating oncologists back in the 1970s and 80s.
How so? What was happening?
Well, we would treat a patient's cancer with chemotherapy, say a vinca, alkaloid, or a taxane, and it would work great at first. The tumor would shrink, but then the tumor would come back, and suddenly the same drugs and even other drugs wouldn't work at all.
The cancer became
Their
resistant.
cancer cells had evolved. They had hijacked their own genes to hyperexpress massive amounts of these pumps on their surface.
So the tumor cell basically builds a defense system against the medicine.
An incredibly effective one. The chemo would diffuse into the cancer cell, and this pump, this P-glycoprotein, would just grab it and spit it right back out before it could ever reach the nucleus to do its job and kill the tumor.
So the resistance was actually just a very, very efficient sump pump.
Exactly. And because these pumps are promiscuous, they don't care much about the shape, they'll pump out a wide variety of structurally unrelated drugs. The tumor becomes resistant to 5 or 6 different classes of chemotherapy all at once, hence multi-drug resistance.
That is both fascinating and, frankly, terrifying.
Eh.
So, okay, we have the hardware. SLCs bring things in using pre-existing gradients. ABCs use ATP to pump things out. Now let's look at the map. Section 2, the geography of transport.
This is where it all comes together. We need to talk about vectorial transport.
Okay, break that down for me. Vectorial implies direction.
Right. Most of the critical barriers in our body, the gut lining, the kidney tubules, the blood-brain barrier, they're all made of sheets of cells called epithelium. To get a drug across that entire sheet, say, from the inside of your gut into your blood, you have to enter one side of the cell and then exit the other side.
Right, you can't just have an entry door on both sides, or the drug would just move back and forth until it reached equilibrium. There'd be no net movement.
Exactly. You need a symmetry. You need an uptake transporter, like an SLC on the basolateral side, the side facing the blood. And you need an afflux transporter, an ABC pump, on the apical side, the side facing the lumen or the waste stream, or sometimes vice versa. This creates that bucket brigade we mentioned that moves the drug in one specific direction.
Let's walk through the body and see this in action. Stop number 1, the intestine. We've just swallowed a pill. It's in the gut lumen. It wants to get into the blood.
Right. So the drug molecule, let's say it's lipid-soluble enough, it passively diffuses into the gut wall cells, the enterocytes. It's trying to cross into the body. But waiting there on the apical membrane, the side facing the gut, is our old friend P-glycoprotein, or MDR1.
And PGP is an efflux pump. It pumps things out.
Correct. So think of PGP as a bouncer standing just inside the club's door. As the drug tries to sneak in via diffusion, PGP recognizes it as a foreign molecule, grabs it, and literally throws it back out into the street, which in this case is the gut lumen. It's a reverse transporter.
So it actively lowers the amount of drug that actually enters the body from the gut.
Dramatically. This is a major reason why some drugs like digoxin or the immunosuppressant cyclosporine have very low and very variable oral bioavailability. It's not that they can't get in, it's that they are constantly being thrown back out.
And this brings up the famous grapefruit juice interaction that Katzum talks about. I feel like everyone knows, don't drink grapefruit juice with your statins, but they think it's just about liver metabolism.
Right, and that's half the story. We usually attribute the grapefruit effect to the inhibition of CYP3A4, the big metabolic enzyme in the gut wall and liver. And that's true. Compounds in the juice called furanocoumarins do that. But grapefruit juice also powerfully inhibits P-glycoprotein in the gut wall.
So you're not just slowing down the breakdown of the drug, you're also handcuffing the bouncer at the front door.
Exactly. Imagine you take a drug like cyclosporine with a big glass of grapefruit juice. You inhibit the PGP that usually keeps the drug out. Suddenly, the bouncer is gone. The crowd rushes in. Way, way more drug gets absorbed into the blood than the dose was calculated for.
And you get a massive toxicity spike.
Yes, all because you distracted the border patrol at the gut wall.
Okay, let's say the drug survives the gut and makes it into the bloodstream. Next stop, the liver, the processing plant.
The liver is the absolute master of vectorial transport. Hepatocytes, the main liver cells, are polarized. They have two distinct faces. They have a sinusoidal membrane, which faces the blood, and a canalicular membrane, which faces the bile ducts.
Okay, so I'm visualizing this. Blood on the front porch and a bile duct at the back door.
That's the perfect way to see it. Now, to clear a drug from the body, the liver first has to get it out of the blood. It uses the OATP family. Remember, those are the organic anion transporting polypeptides from the SLC family on the blood side. OATP1B1 is the big player here. It acts like a vacuum, sucking bulky organic anions like statins from the blood into the liver cell.
So that's the intake, the front door.
That's the intake. Now, the drug is trapped inside the liver cell. It might be metabolized by enzymes there, sure, but to get rid of it completely or to get rid of its metabolites, the liver has to ship it out into the bile. For that, it uses efflux pumps on the canalicular side, the backdoor pumps like MDR1, MRP2, or BSEP, which is the bile salt export pump.
So OATP brings it in the front door from the blood, and then MRP2 pushes it out the back door into the bile.
A perfect one-way street. In the lab, we call cells that do this doubly transfected cells. You need both doors, the indoor and the outdoor, to be working to efficiently clear the drug.
So what happens if the front door is locked? Let's say OATP is blocked by another drug or there's a genetic defect.
Then the statin can't get into the liver at all. It stays circulating in the blood. The systemic levels rise, and that is when you get the side effects elsewhere in the body, like myopathy, muscle damage. The drug is loitering in the blood instead of doing its job inside the liver.
It's so interesting. We usually think of clearance as just breaking a drug down metabolism. But here, clearance is the physical act of moving the drug out of circulation and into the liver cell in the first place.
Location is destiny. If the statin is in the blood, it's potentially toxic to the muscle. If it's in the liver, it's therapeutic for cholesterol. The transporter is what determines that location.
Let's move on to stop number 3, the kidney, the filtration and secretion system.
The kidney is fascinating because we usually think of filtration as a passive process blood being squeezed through a filter, the glomerulus. And that happens for small drugs. But for many, many drugs, the proximal tubule actively secretes them. It literally pumps them from the blood into the urine to speed up their elimination.
This sounds like another bucket brigade, another two-door system.
It is. On the blood side, the basolateral side, you have influx transporters like OAT1 and OAT3. They take up anions from the blood. And here's that amazing mechanistic detail from Goodman and Gilman that I just love. They do this against the gradient by exchanging the drug for a molecule called alpha-ketoglutarate.
Alpha-ketoglutarate, that's a Krebs cycle intermediate, right?
It is. The cell has tons of it. It literally dumps alpha-ketoglutarate out into the blood in order to pull the drug anion in. It's a literal swap. It's bartering at the molecular level.
So the kidney sucks these drugs out of the blood and into the tubule cell. Now it has to get them into the urine.
Right. On the other side, the urine side, the apical membrane, you have our friends, the MRP2 and MRP4, pumping anions out into the urine. And for recanications, you have a very important group called the MAT transporters, the multi-drug and toxin extrusion proteins.
MAT-T, that's a friendly name for a waste disposal unit.
Very friendly. The mates have another cool mechanism. They work by exchanging cations for protons, for H+ ions. They use the natural acidity of the urine as an energy source to push drugs out. This is exactly how we clear things like metformin, penicillins, and many antiviral drugs.
So if you were to block a MAID transporter, the drug gets stuck inside the kidney cell.
Precisely. And it can accumulate there to toxic levels, or it can back up into the blood, defeating the purpose of clearance.
Okay, last stop on our geography tour, the brain, the sanctuary.
The blood-brain barrier, the BBB. The body tries very, very hard to keep things out of here. The endothelial cells that line the brain's blood vessels have tight junctions. They're essentially welded together, so there is no slipping between the cracks. You have to go through the cell.
And I'm going to assume the border patrol is extremely heavy here.
The heaviest. You have massive expression of P-glycoprotein and BCRP right on the blood-facing side of those endothelial cells. Their job is simple. If anything looks remotely suspicious, like a foreign chemical, a xenobiotic drug, pump it back into the blood immediately.
Just access denied.
It's the primary reason why treating brain diseases is so incredibly hard. You can design the perfect drug to target a plaque in Alzheimer's, but PGP sees it as it tries to cross the membrane and just kicks it right back out before it can even cross the threshold.
This is actually a perfect segue into Section 3, when things go wrong. Because that protection at the BBB is the setting for one of the most famous and illustrative drug interactions in all of pharmacology, the loperamide paradox.
I love this case study. It perfectly illustrates the concept of transporters protecting a sanctuary site. So loperamide is the active ingredient in Imodium. It's an opioid.
But we use it for diarrhea. It doesn't make you high. It doesn't cause respiratory depression. It's sold over the counter. Why?
Structurally, it is a potent opioid. It should affect the brain, and it tries to. It's lipid-soluble. It gets into the endothelial cells of the blood-brain barrier. But loperamide is a perfect substrate for P-glycoprotein. As soon as it steps inside the door, PGP grabs it and kicks it right back out into the blood.
So it enters, gets kicked out, enters, gets kicked out. It's like a treadmill to nowhere.
Exactly. It never achieves a high enough concentration to get past that endothelial cell layer and reach the opioid receptors deep in the brain. It only works on the opioid receptors in the gut, which slows down digestion. And that's why it treats diarrhea without the central nervous system high.
So its entire safety profile relies on that one transporter working properly.
Completely. Now, imagine you take that loperamide with quinidine. Quinidine is an old antiarrhythmic drug, but it also happens to be a very potent inhibitor of P-glycoprotein.
You disable the border patrol.
PGP stops working. The bouncer is knocked out. Loperamide flows across the blood-brain barrier completely unchecked. Suddenly, your anti-diarrhea medication is flooding your central nervous system. You get profound respiratory depression. You can actually overdose on Imodium if you block that transporter.
That is terrifying. And it shows that the non-CNS nature of a drug isn't necessarily about the drug structure itself, but about how the body's transporters handle it.
Precisely. It's not that the drug can't cross the barrier. It's that it is actively prevented from staying there.
Okay, let's look at another one we touched on earlier. Statins and myopathy. This is what Goodman and Gilman classifies as clearance organ toxicity.
Right. We mentioned this with the liver's front and back doors. Statins need to get inside the liver to work to inhibit HMG-CoA reductase. OATP1B1 is the influx pump, the front door that gets them there.
So OATP1B1 is crucial for the drug to even work in the first place.
Yes. But let's say you have a patient who is also taking cyclosporine, which we know inhibits OATP1B1, or maybe they're taking gemfibrozil. Or, and this is very common, let's say the patient has a genetic defect, a single nucleotide polymorphism, a SNP in the gene for OATP1B1 that makes their transporter lazy or non-functional.
The front door is stuck, or it's just really slow.
So the statin can't enter the liver efficiently. Two things happen. One, it might not work as well to lower their cholesterol. But two, and much more importantly, its concentration in the blood skyrockets. The drug is just circulating and circulating, and eventually it diffuses into skeletal muscle cells.
And muscle cells do not like high concentrations of statins.
No. High exposure in muscle leads to toxicity myopathy, muscle pain, or in severe cases, rhabdomyolysis. The muscle literally breaks down, releases myoglobin into the blood, and can shut down the kidneys.
So if I'm reading Figure 5.3 in Goodman and Gilman correctly, this is classified as decreased uptake at clearance organs, causing increased systemic exposure.
That's the formal textbook definition. I just call it the drug missed its exit on the highway and crashed into the neighbor's house.
Let's flip that around. What about toxicity that happens at the target organ, the metformin story?
This is the metformin and lactic acidosis link. It's a rare side effect, but it's lethal when it happens. So metformin enters the liver via the OCT1 transporter. That's good. That's where it needs to work. It's then cleared by the kidneys. It enters the kidney cells via OCT2 and exits into the urine via MATE1.
Okay, so it has to flow through the kidney cells to be eliminated.
Right, but imagine you inhibit MATE1, the exit door, into the urine. This can happen with certain drugs, like some tyrosine kinase inhibitors, or even an older drug like cimetidine.
So metformin enters the kidney cell via OCT2, but it can't leave via MAT1. It gets trapped.
It accumulates inside the renal tubule cells to massive levels. We're talking concentrations hundreds of times higher than what's in the blood. And very high intracellular metformin impairs mitochondrial function. The cell panics, it can't make energy aerobically, so it switches to anaerobic metabolism, pumps out tons of lactic acid, and you get systemic lactic acidosis.
So this is a perfect example where blocking the exit door is just as dangerous, if not more so, than blocking the entry door.
Yes. It perfectly illustrates that transporters don't just control blood levels, they control intracellular concentrations. And if you trap a drug inside a specific cell, you can poison that specific cell type.
It's not just about drugs, though, is it? I mean, these transporters didn't evolve to handle statins and metformin.
Not at all. Millions of years of evolution didn't anticipate the pharmaceutical industry. These transporters are there for our own endogenous compounds. BSEP, the bile cell export pump, moves our own bile acids. MRP2 moves bilirubin, the breakdown product of red blood cells. URT1 moves uric acid.
And drugs can completely mess this up, too.
Absolutely. One of the main reasons drugs fail in late-stage clinical trials is DLI, drug-induced liver injury. And very often the mechanism is because the drug inhibits BSEP.
And BSEP is the one that moves bile acids out of the liver.
Right. So if the drug stops that pump, bile acids build up inside the liver cells. And bile acids are basically detergents. They're meant to dissolve fats in your gut. If they build up inside your liver cells, they literally dissolve the hepatocyte from the inside out.
That is a very visceral image.
It is. It's a major cause of liver failure. And look at gout. Gout is caused by too much uric acid. Well, there's a transporter in the kidney called URT1 that reabsorbs uric acid from the urine back into the blood. The body tries to save it. If you have too much URT1 activity, you can get gout.
So we can target that transporter to treat the disease.
We do. Drugs like lesinurad are URT1 inhibitors. We intentionally break the transporter to force the uric acid to stay in the urine so it can be peed out.
That leads us perfectly into Section 4, transporters as drug targets. Because up until now, we've mostly talked about transporters as things that move the drug around. But sometimes, as you just said with lesinurad, the transporter is the drug's target.
This is a huge and growing category of drugs. In neuropsychiatry, it's the basis of almost everything we do.
The SSRIs, for example.
Selective serotonin reuptake inhibitors. The target is SERT, which is SLC6A4. Normally, SERT acts like a little vacuum cleaner at the synapse, sucking up serotonin to terminate the signal. The SSRI drug just jams the vacuum.
So serotonin hangs around in the synapse longer and can signal more.
Exactly. Mood improves. The entire modern antidepressant class works by jamming a transporter.
And what about stimulants?
Amphetamines and cocaine target DIET, the dopamine transporter, and NET, the norepinephrine transporter. Cocaine is a simple blocker. It clogs the reuptake pump, flooding the brain with dopamine. Amphetamines are even sneakier. They actually get carried into the neuron by DAT, and then once inside, they mess with VMAT2.
What's VMAT2?
That's the vesicular monoamine transporter. It's the transporter inside the neuron that packs dopamine into little storage boxes or vesicles to keep it safe until it's released. Amphetamines disrupt this packing process, causing dopamine to spill out into the cytoplasm of the neuron, and then they actually reverse the direction of DAT, the transporter on the outside, to pump all that loose dopamine out into the synapse.
So instead of vacuum, it becomes a fire hose.
A perfect analogy. And speaking of VMAT2, we also target that therapeutically in Huntington's disease. In Huntington's, you have too much movement, this chorea. We can use a drug called tetrabenazine, which is a VMAT2 inhibitor.
So the dopamine can't get packed away into its storage vesicles.
It can't be stored, so it gets broken down by enzymes in the cell. The total amount of dopamine available drops, and the chaotic movements subside. We are treating the disease by intentionally sabotaging the transporter.
Let's look at the kidneys again. The SGLT2 inhibitors. These are absolutely massive in diabetes and cardiology right now.
The gliflozins, canagliflozin, dapagliflozin, and so on. SGLT2 is the sodium glucose cotransporter 2. In the kidney, it's responsible for reabsorbing about 90% of the glucose from the urine back into the blood. The body hates losing sugar. It's valuable energy.
But in a person with diabetes, you want to get rid of that excess blood sugar.
Exactly. So we block SGLT2. The kidney stops saving the sugar. You pee it out. Hundreds of calories of sugar a day. Blood glucose goes down. It's a brilliant mechanism because it doesn't depend on insulin at all. It works even if a patient's pancreas is completely burned out.
And one more, which I found really compelling in the literature, cystic fibrosis.
This is a true triumph of understanding transporters at a molecular level. Cystic fibrosis is caused by a mutation in the CFTR gene, and CFTR is actually an ABC transporter, but it has this weird quirk where it acts as a chloride channel.
Wait, an ABC transporter that acts as a channel? I thought we just said those were different.
It's the big exception. It has the structure of a pump, it binds ATP, but its function is to let chloride flow like a channel. When it's broken, chloride gets trapped inside cells, water doesn't follow, and mucus gets incredibly thick and sticky in the lungs and pancreas.
And the drug ivacaftor, how does that help?
It's called a potentiator. For certain specific mutations, like the G551D mutation, the CFTR protein gets to the cell surface, but its gate is jammed shut. Ivacaftor binds directly to the protein and essentially props the gate open, forcing it to stay open longer. It directly fixes the mechanics of the broken transporter. It has completely changed the lives of patients with that specific mutation.
That is just incredible. It really drives home the point that these aren't just abstract kinetic variables. They are physical molecular machines that we can actually tinker with.
Absolutely. We can jam them, we can reverse them, or in this case, we can even fix them.
Let's move to section 5, genetics, resistance, and regulation. We touched on genetics with the statins. This is the whole field of pharmacogenomics.
This really is the future of precision medicine. We already talked about SLCO1B1, the gene for OATP1B1, and statins. The FDA and other clinical guidelines literally say if a patient has this specific low-function genetic variant, you cannot give them high-dose simvastatin. You will hurt them.
It's not a suggestion anymore. It's a rule baked into the guidelines.
It's a rule. And we see it with other transporters too. Variants in BCRP, the gene is ABCG2, can affect how people respond to allopurinol for gout. We are slowly moving toward a world where you get your transporter genome sequenced before you ever get a prescription.
We also talked about resistance in cancer. That's where the MDR name came from. But is resistance always about a pre-existing genetic difference? Or can the body change the number of transporters it has on the fly?
That's the critical concept of induction. The number of transporters isn't static. The body can build more of them if it feels like it's being threatened.
Threatened by what exactly?
By foreign chemicals, by toxins. We have these sensors inside our cells, these nuclear receptors like PXR, the pregnane X receptor. Think of PXR as the watchman or the smoke detector inside the cell.
Okay, so the watchman detects a strange chemical it doesn't recognize.
Right. When a drug, like the antibiotic rifampin, binds to PXR, PXR travels to the nucleus and tells the DNA, we are under attack by a foreign substance. Build more armor.
And the armor is?
P-glycoprotein and CYP3A4. It upregulates both the metabolism enzyme and the efflux pump at the same time. This is what we call the double whammy of detoxification. The body coordinates its response.
Can you give an example of how this plays out for a patient?
The classic example is rifampin and digoxin. Rifampin is a potent PXR activator. If you put a patient on rifampin, within a few days, their body starts churning out way more PGP.
So if that patient is also taking digoxin for their heart,
the PGP levels in their gut wall and kidney tubules just skyrocket. They start pumping the digoxin out so fast that its blood levels can drop to near zero. The drug just stops working completely, and that is a drug-drug interaction caused by making more transporters.
So we have inhibition, which is blocking the door, and we have induction, which is building more doors.
Exactly. And the key difference is the timing. Inhibition is immediate. You take the inhibitor drug, the interaction happens right now. Induction takes time, days to maybe a week or two, because you have to physically synthesize new protein.
We're in the home stretch now,
Yeah.
section 6, the clinical and regulatory synthesis. So with all this complexity, what does a body like the FDA say about all this?
The FDA takes this very, very seriously now. It's no longer an academic curiosity. When a company develops a new molecular entity, an NME, they must screen it for interactions with a whole panel of key transporters. PGP, BCRP, OATP1B1, the OATs, the OCTs.
It's a non-negotiable safety requirement.
It is. You have to answer the questions. Is my new drug a substrate for these pumps? Will it get blocked by other drugs? And is my new drug an inhibitor of these pumps? Will it kill someone who is taking statins? You can't just guess anymore. You have to do the experiments.
So for the clinician listening to this or the student, what's the reasoning framework? When should their internal transporter alarm go off?
I look for three main clues. The first is what I call the oral paradox. If you give a drug orally and it has a surprisingly low or variable effect, but it works perfectly fine if you give it IV, you should immediately suspect PGP in the gut is pumping it out.
Okay, clue number 2.
The metabolic mismatch. If two drugs cause a major toxicity when given together, but you look it up and they are metabolized by completely different enzymes, you should suspect a transporter interaction. That's the loperamide and quinidine story. No metabolic overlap, pure transporter inhibition.
And the third one?
This one is a bit more subtle, the renal twist. If a patient develops renal failure, and suddenly the toxicity of a drug that is cleared by the liver goes up.
Wait, explain that last one. That's really counterintuitive. If the kidneys fail, why does a liver-cleared drug become more toxic?
It's because of uremic toxins. When the kidneys fail, waste products build up in the blood. Many of those toxins are organic anions, and those uremic toxins compete for transporters all over the body. They might start blocking the OATP transporter that's responsible for getting that liver drug into the liver. So kidney failure can actually cause liver drug toxicity via transporter crosstalk.
That is incredibly complex. It really highlights that all the organs are connected by this shared transport network.
And it brings us to this final, really important concept, the extended clearance concept. We used to think liver clearance was just about metabolism, but the new equation is clearance equals uptake plus metabolism plus biliary secretion. It's a 3-step process.
And the rate-limiting step, the bottleneck, might actually be the uptake.
Exactly. The pharmacologists talk about the intrinsic clearance of the uptake transporter, what they call PS-INF. If the front door is locked, if that uptake rate is low because of genetics or an inhibitor drug, it doesn't matter how fast the enzyme inside the cell works. The enzyme has nothing to do. The drug is stuck outside. The transporter is the boss.
Deep breath. That was a lot. But I feel like I can actually see the traffic now, not just the roads. Let's head to the outro and try to recap this.
Let's simplify it right down. ABC equals pumps, active transport. Afflux, they burn energy. They are the sump pump. SLC equals carriers. Facilitated transport, mostly influx. They're hitching a ride. They are the turnstile.
Vectorial transport is the system that moves drugs across barriers. The gut, the liver, the kidney, the brain. It always needs an entry door and an exit door.
And inhibition of these transporters is what explains so many of the mystery toxicities. Loperamide getting into the brain, statins getting stuck in the blood and hurting the muscle, metformin getting trapped in the kidney cells.
And finally, as always, a provocative thought to leave you with.
We spent this entire hour talking about drugs, about xenobiotics. But remember, these transporters evolved for us. They evolved to handle our own vitamins, our hormones, our bile acids, our neurotransmitters. When we block a transporter to manipulate a drug, like when we give a PGP inhibitor to boost another drug's levels, what are we doing to the body's own delicate housekeeping?
That is a heavy question.
I mean, think about it. What endogenous toxins are we accidentally trapping inside the brain when we block PGP? What hormones or signaling molecules are we preventing from leaving the liver? We are only just beginning to scratch the surface of understanding the endogenous cost of messing with these ancient fundamental systems.
A very sobering thought. We're not just tampering with the traffic, we're tampering with the city's entire infrastructure.
Exactly.
All right. To really nail this down, you need to see the diagrams. Go to Goodman and Gilman, Chapter 5. Look at the pictures of the proximal tubule and the hepatocyte. You need to visualize that bucket brigade.
And then check Katsung Chapter 67 for the clinical interaction tables. It's a lifesaver for seeing how this plays out in practice.
Thanks for listening. Keep your influx high.
And your efflux efficient.
See you next time.